Hi everyone, I am Grant na Alameda. You can just call me Sir G, and you're watching the Side Talk.
Sorry, but I'm number one.
For this video, we're gonna talk about protons, electrons, and atoms.
Atoms make up everything, but what makes up of atoms? Yes, protons, electrons, and neutrons. There are 118 different kinds of atoms, which are each the smallest parts of an element.
If we observe gold, carbon, oxygen, they have different properties that don't look. But why they are so different?
Well, it comes down to what's inside their atoms. Atoms are made in just three types of particles called protons, electrons, and neutrons. Protons are positively charged subatomic particles that reside in the nucleus. Neutrons are negatively charged subatomic particles that reside in the nucleus. And lastly, electrons are negatively charged subatomic particles found in the electron shell surrounding the nucleus.
Now, we're going to talk about how to calculate the number of protons, neutrons, electrons in an atom, and ion.
Let's use sodium as an example. On periodic table, you might see look like this. As you can see, there are two numbers. The smaller number is known as atomic number, which is equals to protons. The larger number is known as average atomic mass. Now, let's talk about formulas we need in order to calculate the number of protons, neutrons, and electrons. Let's start with protons, which is equals to the atomic number. Neutrons, which is equals to mass number minus atomic number. And lastly, electrons, which is equals to atomic number minus the charge of species. Let's take for example 23 mass number and 11 atomic number, which is the sodium. To get the proton, so we will identify the atomic number, which is 11. So we're gonna put it down here, 11. For the neutrons, we will going to use this formula. The mass number is minus 2 atomic number. So 23 minus 11 is equals to 12. Now to get the electrons, we will use this formula. Atomic number minus charge. So 11 is our atomic number, and for this situation there is no charge. So we're going to put it here 0. So the answer is 11. Another example, 27 mass number and 13 atomic number, which is an aluminum and has 3 positive charge. Now to get the protons, we will identify the atomic number, which is 13. Now to get the neutrons, we will identify the mass number and the atomic number. 27 and 13. 27 minus 13 is equals to 14. Now to get the electrons, we will identify the atomic number and the charge of species. So the atomic number is 13 minus the positive charge, which is 3, from minus positive 3 is equals to 10. Another example, 33 mass number and 16 atomic number, which is sulfur, and it has 2 negative charge. Now to get the protons, we will identify first the atomic number, which is 16. For the neutrons, we will identify the mass number and atomic number, which is 33 and 16. 33 minus 16 is equals to 17. Now for electrons, we will identify the atomic number and their charge. So 16 is our atomic number minus negative 2. Negative 2, or it can be addition, which is, so the answer is 18.
Now, we're going to talk about emission and absorption of light. Spectrum is simply a chart or a graph that shows the intensity of light being emitted over a range of energy. Emission spectra is when energy is absorbed by the electrons of an atoms. Electrons move from lower energy levels to higher energy levels. The emission spectrum is formed by the frequency of this emitted light. On the other hand, an absorption spectrum is constituted by the frequency of light transmitted with dark bands, when energy is absorbed by the electrons in the ground state to reach higher energy states. Emission spectra versus absorption spectra. The main difference between emission and absorption spectrum is that an emission spectrum has different colored lines in the spectrum, wherein an absorption spectrum has dark color. More difference between absorption and emission spectrum will be given. In emission spectra, it produced when atoms release energy, while on the absorption spectra, it produced when atoms absorb energy. In emission spectra, it comprised colored lines in the spectrum, while in absorption spectra, it comprised dark lines or gaps in the spectrum. Emission spectra is helpful in figuring out the composition of a certain matter, while an absorption spectra can be used to figure out the ability of certain objects to retain heat and its absorption level. Lastly, emission spectra can meet all the colors in all electromagnetic spectrum, while the absorption spectrum can have a few colors missing due to the redirection of absorbed photons. When the light shines on the metal, electrons can be ejected from the surface of the metal, a phenomenon known as photoelectric effect. Yes, we're going to talk about the photoelectric effect. This process is also often referred to as photoemission. Electrons that are ejected from the metal are called photoelectrons. In terms of their behavior and their properties, photoelectrons are no different from other electrons. These photos simply tells us that the electrons have been ejected from the metal surface by incident light. In photoelectric effect, light waves or red wavy lines are hitting a metal surface cause electrons to be ejected from the metal. To explain the photoelectric effect, 19th century physicists theorized that the oscillating electric field of the incoming light wave was hitting the electrons and causing them to vibrate, eventually freeing them from the metal surface. Scientists also believe that the energy of the light wave was proportional to its brightness, which is related to the wave's amplitude. In order to test their hypothesis, they perform experiments to look at the effect of light amplitude and frequency on the rate of electron ejection, as well as the kinetic energy of the photoelectrons. Based on the classical description of light as wave, they made the following predictions. One of these is the kinetic energy of emitted photoelectrons should increase with the light amplitude, and the rate of electron emission
which is proportional to the measured electric current, should increase as the light frequency is increased.
To help us understand why they made these predictions, we can compare light wave to water wave.
Imagine some beach balls sitting on a dock that extends out into the ocean. The dock represents a metal surface, the beach ball represents electrons, and the ocean waves represent light waves. If a single large wave were to shock the dock, we would expect the energy from the big wave would send the beach balls flying off the dock with much more kinetic energy compared to a single small wave.
This is also what physicists believe would happen if the light was increased.
Classical physicists also predicted that increasing the frequency of light waves would increase the rate of electrons being ejected and thus increase the measured electric current. Using our beach analogy, we would expect waves hitting the dock more frequently would result in more beach ball being knocked off the dock compared to the same size waves hitting the dock less often.
Now that we know what physicists thought would happen, let's look at what they actually observed experimentally. When experiments were performed to look at the effect of light amplitude and frequency, the following results were observed.
The kinetic energy of photoelectrons increases with light frequency. Electric current remains constant as light frequency increases. Electric current increases with light amplitude. And lastly, the kinetic energy of photoelectrons remains constant as light amplitude increases.
These results were completely at odds with the prediction based on the classical description of light as wave.
In order to explain what was happening, it turned out that the entirely new model of light was needed. The model was developed by Albert Einstein, who proposed that light sometimes behave as particles of electromagnetic energy, which we now call photons. Photons are particles of light. This explains the photoelectric effect because an electron is ejected. When struck by a singular photon with sufficient energy, it only takes one photon. Even the faintest beam above a certain frequency will be able to do. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy of the photon can be given by the following equation.
Now, let's talk about atomic line spectra and energy level spectra.
What are atomic spectra? Atomic spectra are defined as the spectrum of the electromagnetic radiation emitted or absorbed by an electron during transitions between different energy levels with an atom.
When electrons get excited from one energy level to another, it either emits or absorbs light of a specific wavelength.
The collection of all the specific wavelengths of the atom in a given set of conditions like pressure, temperature, and etc. are the atomic spectra of atoms. From the image above, it is evident that the atomic hydrogen emission spectrum is divided into a number of spectral lines with wavelengths given by the Rydberg formula. Using the Rydberg formula, it becomes easy to calculate the spectral lines. This is the Rydberg formula. The observed spectral lines in the hydrogen emission spectrum are due to the atomic transitions between different energy levels. The spectral series are important in astronomical spectroscopy. Atomic spectroscopy is the study of electromagnetic radiation absorbed or emitted by atoms. It is used for identifying the spectral lines materials used in metallurgy. It is used in pharmaceutical industries to find the traces of materials used. And lastly, it can be used to study multidimensional elements.
We are done now with all of our discussions. Now, let's proceed to our quiz. Let's check out if you really understand our discussion. Prepare a one sheet of paper and a black pen. Now, let's check your answers. That's all for this video and thank you for watching. I am Grant Alameda, you can call me Sir G, and you're watching The Side Talk.